Good evening. We are now on the 12th presentation. Now, in this presentation and the coming presentation, we will be evaluating what are the materials that will be able to possibly succeed in decomposing water to the extent of at least 30%. That is our motive in presenting these two lectures. And then, so as usual, you can ask for questions, remarks, and other things. It should be useful to you as well as to me. So briefly recapitulating what we have done, all other things we have done, we have specified certain conditions for the effective use of the materials. That is, one is the photo-generated electron hole pair. Why I am mentioning this is the generation of the photon, the hole and the electron, the exciton, takes a time scale of femtosecond or picosecond, whereas the charge transfer to the substrates at the interface takes the time scale of microsecond or nanosecond. This is the reason why the lifetime of the electron hole pair has to be longer, so that they will be useful in the interfacial reaction. This is one aspect which we have not realized, but we have number of times shown this in a picture, in a figure, but we have not talked about it. Then other than that, the reproducibility and the photo hydrosolubility and photo corrosion, all those things we have already mentioned. Then we also mentioned certain governing principles that has evolved. One of them is layered material. Second thing is the D0, D10 configuration, and also the band gap of the semiconductors. So now what we are talking about is solar energy itself can be used in number of ways. We can use it in the heat. We have already talked about it. When we take it in the form of the heat, then it will be each step that is involved from solar energy to heat to mechanical energy to electricity. Then you have to use hydrolysis. So this is one route. But what will happen is, this is 0.3, this is 0.3, this is 0.3, so it will become 0.027% only. You can also use solar energy to produce the biomass, photosynthesis, and then convert the biomass into hydrogen. This route we are not discussing, but we should, at a later stage, if necessary, we will look at the biomass, hydrogen from biomass. But what we are looking at it is solar energy directly using the photolysis. Okay, photolysis, not photochemical or photoelectrochemical. So now when we take the photoelectrochemical generation of hydrogen from water, the absorption of light near the surface of the semiconductor creates the electron hole pair. If it is near, the diffusion time will be less. Holes, minority carriers, drift to the surface of the semiconductor photoanode, where they react with water to oxidize the produce oxygen. Electrons, majority carriers, are conducted to a metal electrode, typically platinum, or counter electrode, where they combine with the H+ ions in the electrolyte solution to make a H2. Transport of H+ from the anode to the cathode through the electrolyte completes the electrochemical circuit. The reaction is two photons plus water giving rise to H2 plus O2. All these things we have already done. That is why I am going a little fast. But what we are worried about is, if I were to bring the electron or the hole, okay, very near to the conduction band or the valence band, how I will be able to transfer that charge to the substrate? That is the question. And in what scale it will be before the recombine. Second thing is, we have already talked about it, that the reduction potential of the H plus ion and the oxidation potential of water to give oxygen, their potentials should saddle between the conduction band and the valence band. Only few semiconductors are the possibility. For example, you take gallium arsenide, it can evolve hydrogen because its band gap is 1.4. The conduction band is more negative with respect to hydrogen evolution potential, but the valence band is less positive with respect to the oxygen evolution potential. So this cannot give rise to oxygen evolution. Gallium phosphide is possible, but the oxygen evolution will be difficult. Now, if I were to take cadmium selenide, it is possible to give both. Cadmium sulfide, it will be giving a rise to both. Zinc oxide will give you the both. Whereas Fe2O3, the hydrogen evolution is not possible, but oxygen evolution is possible. WO3 also are the same thing. SNO2 also is the same thing. Titanium dioxide can give rise to both, and silicon carbide can give rise to both. So now, why we have shown this, the diagram is, and the relationship between the absolute vacuum potential with respect to the electrochemical potential, we have already shown that the zero of the electrochemical potential corresponds to minus 4.5. Okay, this will be vacuum level is 0. With respect to it, all of them are negative. Whereas the 0 is here in the electrochemical cell, therefore potentials above is negative and potentials below are positive. Why we have shown this diagram is, what type of materials we can try. Okay, one is oxide materials, that is very clear. Another one is, we can use oxysulfides, oxynitrides. So therefore oxygen is component, but we can also use the elements like nitrogen, sulfur, phosphorus, gallium phosphide we showed here, arsenide, all those things. So what is the thing? Okay, in this picture we have only shown oxides and the 3,5 semiconductors: gallium phosphide, gallium arsenide, cadmium sulfide, like that. Desensitization is something to do with the lifetime of the charge carriers. Okay, that is what we have not done. If it is necessary, we will do that. So now, if I were to take all these things into account and try to make a PEC hydrogen evolution cell, then its efficiency is always less. Okay, the production of hydrogen is demonstrated, but the efficiency is less. The efficiency and the lifetime are interrelated to each other. So what we have done so far is the band gap engineering to match water redox potentials and achieve high solar efficiency. That is what I said is, the hydrogen evolution potential and oxygen evolution potential must saddle between the conduction band minimum and the valence band maximum. That is what is called the band gap engineering. Then we have also understood fundamental understanding of the electrode-electrolyte interface. We have already seen that electrode-electrolyte interface can give rise to some barrier. This barrier can be of two types. We will not worry about it: ohmic type and the Schottky barrier. And the charge transfer at the barrier is what is controlling the thing. So what we have to do this way is, when we try to increase the charge transfer, the photocorrosion can occur. Okay, therefore we have to reduce the corrosion and increase the water splitting reaction. So here we are showing you gallium arsenide, germanium, and gallium indium phosphide. Okay, the gallium content in the indium gallium nitride alloy is shown here. You can see that the band gap is very tuned, linearly varying from the value to the value around 4. Okay, energy electron volts. So now the direct energy band gap of indium gallium nitride covers most of the solar spectrum. Multi-junction solar cell based on this single ternary could be very efficient, because we have already told that elemental semiconductors is one of them which we should do, because we can continuously vary the band gap. So now here what we are showing here is the indium gallium nitride, gallium arsenide nitride, and in comparison with the titanium dioxide. Now if depending upon the value of this X, indium 1 minus X, gallium X nitride, okay, when it is 0.6, when X is 0.6, the band gap is nearly 2 electron volts. The same way gallium arsenide, when X is equal to 0.2, the band gap is around 2 electron volts. Whereas in the titanium dioxide, the band gap is 3.2. So therefore, the conduction band and valence band edges straddle the H plus H2, O2, H2O redox potential. They can be made with the optimal band gap of 2 electron volts. We have shown here. Okay, 2 electron volts, 2 electron volts. In the same semiconductor, with suitable substitutions, we can go. They have superior corrosion resistance compared to other semiconductors of similar energy gaps. Okay. So therefore, I hope you understand the elemental semiconductors will not undergo so easily the corrosion. So this is only to show you how the current, photocurrent, is in varying with respect to pH. Okay, because photocurrent is also potential dependent. Therefore, for each pH, potential will be by 59 millivolts. It will shift. We will not worry about all of them. So we are showing here at pH 4, pH 2 by 4, 7, and 14. So we are at the peak of the oil age, but the beginning of the hydrogen age. Anything else is an interium solution. Okay, if we say natural gas or coal, or all of them are only for a period, like the petrol or diesel, or the crude oil. It will also last for a time. The transition will not be very easy. It will be very messy, because we have established a oil-based economy. So to change this from oil-based economy to hydrogen-based economy, it will take some more, and we have to dismantle many things and erect many things. Will take many technological parts, and also the another point that we should remember is we understood that the oil as the fossil fuel is injurious or environmentally not friendly after 70 or 80 years of its use. The same way, if we start using hydrogen, we will be able to, first 60, 70 years, we will not be able to see its bad effects, but it may have bad effects, and it will be ultimately, we have to think the same way as fossil fuels. Anyway, we will not worry about it at this moment, but the future will be hydrogen fuel cells. General Motors absolutely sees the long-term future of world being based upon hydrogen economy. So these are all only to show. This we have shown already, therefore we will not go into all of them. Now, when we want to do, instead of directly going into the water electrolysis, whether it is possible to go through a photovoltaic device. So to take the solar panel and harness the photovoltaic and use the photovoltaic for electrolysis of water. Okay, photo-electrochemical based direct conversion systems combines a photovoltaic system. I hope you are saying that the red is the photovoltaic system, the panels, this is the collectors. So combining a photovoltaic system, light harvesting, and an electrolyzer water splitting into a single monolithic device. So we can make, instead of this, even though it is shown, all of them can be put in one piece. Electrolysis area approximately that of the solar cell. The current density is reduced. Balance of system costs are reduced. This is a statement for economists, but we will not worry at the moment. So what is the advantage here is the semiconductor processing is not very much, because electrolyze the photovoltaic is the silicon semiconductor. So therefore, silicon semiconductors, we know very well, we are having already about 20%, 25% efficiency or 30% efficiency. But that is not the point. So the chemical potential to electrochemical potential, chemical potential that we get is 1.3, but the electrolysis potential is 1.9. So that itself is 65% only efficient. Coupling to a 12% photovoltaic array gives 12% into 65% will be 7.8%. So this is all the net efficiency that we can get. If I were to direct conversion efficiency with a base of 12%, operating at an equivalent of 1.54 volt instead of the 1.9 volt, then I can get 10% efficiency. Okay, equivalent electrolysis efficiency of 85% equals to a 30% decrease in the coverage area. Okay, so we have understood all of them now, at least. So what is the material and energy requirements is the question. One is the band gap, we have understood that. Band edge overlap. Okay, the band edge overlap means the band edge of the semiconductor and the electrolyte, and the fast electron transfer. It should be at least coming to picosecond or femtosecond. At the moment only microsecond or nanosecond. So what we are looking at it is all these three: band gap, edge overlap, fast electron transfer or charge transfer. All of them must be simultaneously present. In addition to that, the material must be stable. The most photochemically stable semiconductors in aqueous solution are oxides, but their band gaps are either too large for efficient light absorption. Their semiconductor characteristics are poor because of the diffusion length or diffusion of the charge carriers. For reasonable solar efficiency, the band gap must be less than 2.2 volts. Okay, 2.2 electron volts. Unfortunately, most useful semiconductors with band gaps in this range are photochemically unstable in water, whereas titanium dioxide is stable in water. In contrast to metal electrodes, semiconductor electrodes in contact with the liquid electrolyte have fixed energies where the charge carriers enter the solution. So even though the semiconductor electrode may generate a sufficient energy to effect an electrochemical reaction, the energetic position of the band edges may prevent it from doing so. For spontaneous water splitting, the oxygen and hydrogen reactions must lie between the valence band and conduction band edges. This is almost never the case. We have already seen this picture we have shown. Okay, only few semiconductors are saddling between the conduction band edge and valence band edge, are saddling between the hydrogen evolution potential and oxygen evolution potential. Now what we have seen is catalyst is the hydrogen, the oxides. Okay, it should evolve stoichiometrically the oxygen, and then the transparency of the semiconductor to the photons must be there. Band edge engineering, semiconductor hybrid systems, low cost design features. So now one question we have to answer. The question is, if we are talking about water shortage, and we are talking about water being the use of the fuel. So what is the situation is the question. Okay. Now the global energy demand of the earth is 4 into 10 to the 20 joules per year. Okay, that means the 1 gigajoule can be obtained from 90 liters of water. All these things, numbers may not mean anything to you, but anyway, I will tell you the water needed for producing 4 into 10 to the 20 joules is 10 to the 13 liters. Now, the water that is available in the ocean is 10 to the 21. So you can see that even if you assume that 10 to the 13 liters are required, we have very many excess of maybe 10 to the 8 or 10 to the 10% of water. Actually, the oceans, if I were to take some 10 to the minus 5% of water in the ocean is enough. Or if I were to take the annual rainfall, it is 10 to the 17. What we want is 10 to the 13. So therefore, you see, even if I were to take 0.01% of the rainfall for the fuel production, that is enough. So therefore, we should not be carried away with the idea that we are already water shortage, therefore we will not be able to use water and decompose water. That is not the criterion at all. Now, few other points that we have to quickly mention is PEC technology is based on solar energy, which is a perpetual source of energy, and water, which is a renewable source. PEC technology is environmentally safe with no undesirable byproducts. PEC technology may be used on both large and small scales. You can use it in your house, you can use it for a community. PEC technology is relatively not complicated. It is very clear to us. So now the picture that is shown here and the explanation they are already given, therefore we will not spend much time. Only other thing we have to tell is whether we are going to use a two electrode system or 3 electrode system. Okay. So what we have understood now is what is the type of semiconductors that we are using, what is the donor density that is required, and what is the flat band potential. Flat band potential is, we have already seen the bands are bent. Bent means the energy levels are altered, that is all. So when the energy levels are not altered at the interface, then the position of the band is called flat band potential. Now this is very much important for us because we have already seen that at the interface the band edges should be overlapping with the band edges in the electrolyte. So now, desired properties of an ideal semiconductor photocatalyst is already, all of them I have been told, but anyway I will quickly go through them. Small band gap to absorb up to 600 nanometers, ability to work without the sacrificial agent, only low cost, direct band gap, the better light absorption, high quantum yield, high efficiency without expensive co-catalyst, long-term stability, compounds with environmentally friendly elements. So these are the very important characteristics of that. So here what we are shown is, you can see the black dots are the top of the valence band and the white dots are the bottom of the conduction band. So you can see many semiconductors can give rise to oxygen evolution but not hydrogen evolution. Okay, various sulfides and oxides. We have already said oxynitrides, oxysulfides, all those things can be tried. So this is only to show you that it has another approach that is possible, that is the cleaning of the environment. We are not going to do that here, but it is also possible. So the term functional designation photo-mediated redox reactions such as photocatalytic water splitting, environmental pollutant abatement, and organic synthesis. Ultimately, these applications were fueled by the expectation of efficiently harnessing and utilizing freely available solar energy. Freely, I have already told you, it is not freely available, but from our packet we are not paying them. That is the thing. So now on the right hand side we are showing you suspended particulate system in a photocatalytic mode. In the left hand side we are showing the photo-electrochemical system. Okay. In the center picture we are showing the energetics of these two. These are all already we have discussed, therefore we are not going to do that. So to show you something about how this area is developing in other countries, okay, including India, okay. I hope you are able to see India is the yellow thing, okay. So you can see we are producing nearly about 1,000 papers on this per year. Okay. Anyway, China is leading in all of these things. So therefore, if anything has to happen, it has to happen in Asian continent. Okay, this is not necessary for us. Now we have to, what are the things that we have to understand in this is understanding the charge transport within the semiconductor and between the semiconductor and the electrolyte. This is one thing which is slightly different from the conventional electrochemistry. We have to look at that sufficiently. Then identifying the reaction mechanism, that is how the charge transfer is taking place. Designing in an innovative photocatalyst and engineering photon delivery to the photocatalyst. This is only to show you in what all possible ways this can be used. This we have already shown. We will not worry about it. It can, this same thing can also give rise to a OH radical, which will give rise to pollution removal and other things. Chemisorped oxygen can be reduced upon UV illumination, where it remains either in the dissociated state or dissociates to produce atomic species, or undergo hole mediated desorption as molecular oxygen radical. Photocatalytic mechanism is intricate, plus the photocatalyst material and its history. Okay, we will see later on. Photocatalytic materials and substrate specificity 10 picoseconds, and the diffusion length must be of the order of 2 to 4 nanometers. Okay, we will not worry about all other things, we have already talked about them. One of the most fundamentally intriguing issues in titanium dioxide photocatalysis is proposed synergy effect between anatase and rutile, the two most important polymers of that. The best catalyst is 13% rutile and 79% anatase. You can also use the metals to reduce the Schottky barrier and evolve the hydrogen. Reduced graphene oxide, good electron transport, therefore it can be used for the absorption of the pollutant or the charge carriers. Z scheme is another thing. Organic dye sensitization is another thing. All those things are we have already done. What we are trying to say, why are we repeating is, we have to understand what is it that is stumbling block from 1972 onwards till today, why we are not able to achieve the 25% or 30% threshold efficiency. So we can reduce the band gap or extend the solar radiation limits, whatever possible way we have to do that. And then we have already talked about it. This is another thing that we have to understand. We should not be going on taking any material and go on altering it. So each element in the system that we are designing has got a role. Okay, I will tell you what is this. So, for example, if I were to take a sodium tantalate, I take sodium tantalate. Sodium is not taking part in the reaction, but it is only for the crystal structure of the compound, of the perovskite structure. Titanium is titanium 0, okay, titanium 4 plus is for the photon absorption. Okay, I hope you understand. So therefore, in the same way, when I substitute oxygen by nitrogen or carbon or sulfur, what we are doing is we are controlling the stability of the system. It should not be very highly stable. It should not be very highly unstable. Both are not good. So therefore, what it means is that in designing the materials, we have to think what element of the periodic table should be used for what purpose. We will have a separate presentation on that later on. Then we have already talked about it, is that the anisotropy, that is lower order or one-dimensional, two-dimensional materials are better than the three-dimensional materials. We have already demonstrated that. So we will not to worry about it. Then another thing is, we have not talked about it, but I should have talked about it, is spinels is also, other than the perovskites, spinels also are similar to perovskites. Many combinations are possible. A dash B dash O3, A B2O4 is the spinel. So now spinels are also possible, but the problem with the spinels is, I have already talked about it, the ionicity of the bonds are very high. So therefore the spinel systems, only very few spinel systems can be useful. So one has to examine these spinel systems also. Anyway, all these things we have done, the phase sensitiveness of that and all that. Okay. So now, the growth of heterogeneous photocatalysis has been and will continue to be application-driven, supported by strong process fundamentals. Solar water splitting and environmental remediation, if you are looking for pollution control, which are the mainstay applications, will continue to serve as important platforms for showcasing photocatalytic technologies, as well as motivation for establishment of relevant fundamental knowledge. In addition to photocatalytic conversion of carbon dioxide to fuels and other useful chemicals, is expected to be a dominant area and contribute new knowledge, be it in reaction mechanism, material research design, or reactor design. All these things are relevant for water decomposition also. Whereas success in pursuing the different areas of photocatalytic applications are highly rewarding, it is critical to remember that establishing fundamental depth in photocatalysis is the shared responsibility of scientists and engineers alike. We have not yet understood. Scientists have understood certain static phenomenon, and the engineers are understood how to make it into a device. But the interface, that what is the electrode electrolyte interface, and what is the mechanism of the charge transport across these. See, we know the migration of the charge carriers within the semiconductors. We know the charge carrier combination in the electrolyte, but the combination, the charge carriers from the semiconductor to the electrolyte or to the substrate, is what is the problem today. So therefore, I will stop here and allow you to ask some questions. These are all various things. We will not worry about it. So you can ask some questions if you want.